last week, you remember we started doing inverse Laplace transform, and we said that the significance is, you will see in later stages, we solve any system using Laplace because it poses ease for us to solve certain system with the Laplace transform, but then we want to see that system again in time domain, so that's why we apply Laplace transform, and then finally we take inverse Laplace transform. And like we have done Fourier, so we do Fourier transform, inverse Fourier transform, but in this case, finding inverse Laplace transform using formula is a difficult task, so that's why we said that we're going to find it by inspection. What does inspection mean? Once we have Fourier transform Laplace transform for any system, for example, if we have 1 by s, so by inspection we can say that 1 by s would be for u of t. Similarly, if we have something finally s divided by s square plus omega square, we can say that okay, this is for this inverse Laplace transform would be cos of omega t, and so on. If we have any shift, for example, if you have 1 by s plus a square, so we know that 1 by s square is for t, and if you have e power minus a multiplied by it, so it would be a shifted term. We moved on and we solved one of the example in which it was we had distinct roots. So sometimes you get equation in this form, sometimes you directly get your transfer function in this form, and in this case we said that we need to apply partial fraction. Since they are distinct roots, so what we need to do, we simply need to write this whole equation. While we are doing that, we want to split it, because we know that if we get something divided by s plus 1, I know it's e power minus t, something divided by 2, so we want to split that. So we split it a divided by this, b divided by this, c divided by this, but now the point is that how to find a, b and c. And for distinct roots, we said that we simply multiply this term across, and finally you get something like this. So in the very first, in this case, when you multiply, s plus 1 would be cancelled and you are left with these two. Similarly here, s plus 2 cancel, and so on. And finally, for distinct roots, what you do, you take each one of it. For example, s plus 1, you put it equals to 0, and you get s equals to minus 1. So you put this 1, then then you go for s plus 2 equals to 0, and similarly s plus 3 equals to 0, and this is how you move towards finding the finding the a, b and c for partial fraction. And once you have a, b and c, which were minus 2, 3 and 1, finally you know that we can simply say that this is e power minus t, this is e power minus 2t, and this is e power plus 3t. So this is how we find Laplace transform when we have distinct roots. And then we also solved one of the example where we were having repeated roots. In case of repeated roots, we said if you have repeated roots, what you need to do, again, since you have square, so you will be writing a divided by s plus 1 square, then you will reduce the power, then write by b, and then c is simple c divided by s plus 2. Again, in this case, the very first step is similar to the previous case. You just cross multiply it, and you finally get an equation. We solved these examples as well in the last class. But in this case, you don't need to put roots equals to 0, for example, in case of distinct root. However, in this case, you will solve this equation and separate each s powers. For example, you will separate s squared, you will separate s, and again when there's s power 0, and then you compare the two sides, and solving this you will get your equation, your ABC, and then finally equation. So it means that for repeated roots you don't need to put s equals to something. Instead, you need to solve equations, you need to equate your right hand side with the left hand side, and from there you will get few equations, and then by solving those equations simultaneously you can get your answer. Now is an example where we're going to solve repeated roots. So let's do that. So we have an example. So we have repeated For phase test, one of the question would be from this. So we have f of s equals to 2s plus 104 divided by how do you we usually find if the roots are complex or not? We simply solve this equation for its roots, right? Using algebraic, using quadratic equation, which is if you want to find root, it would be x equals to minus p plus minus under root p squared minus 4ac divided by 2a. This is how we find roots for an equation. And if you're going to find roots for this equation, you will see that these are repeated roots.
Okay, but you would, if it was complex, you would need to use the determinant to check, right? If it's negative under the root or not.
Yes. So when you're going to put this everything in this, you will get finally that you have a negative sign inside the loop, and which will bring you. So clearly, if I roughly look at this equation, so you can see that you have b this. So if I put it here, so you have, so this is your a, b, and c. So a is 1, b is 4, and c is this. So if I put it here, a is minus 4, plus minus under root a is 4, here minus 4, a is 1, but c is 104, divided by 2, and a is 1. So it would be minus 4 plus minus under root 16 minus, how much is this? 104 times 4?
416.
Sorry, how much?
416.
So now if you solve it, it would be plus minus 4, this would be minus 400 divided by 2. Right? So it would be minus 4 plus minus root minus. Right, so we know that for 400 we know we can write it as 20 square, but still we have a negative sign with it. So I can split it as, if I remove the root, so on under root minus 1 would stay, and for 20 the root and square would cancel, it would turn out as 20. But I know that this would be minus 4 plus minus j 20 divided by 2, which would be minus 2 plus minus j 10. So it means that we have complex root. And even if you don't want to solve this, if you are not asked to find root, you don't need to solve it. Just directly looking at here, I can see that it will turn out as a negative sign, because 16 minus, the minus term is bigger, so it means that I will be getting a minus sign inside root, and when we get a minus sign inside root, it means that we will get something under root minus 1, so we will get a complex number. So it means that here you have two roots, one is minus 2 plus j10 and another is minus 2 minus j10. So these are the two roots for your this equation, which is only this part. So it means that now we have complex roots in this case. So how are we going to solve it? So we'll write it as f of s equals to 2s plus 104 by s into s square plus 4s plus 104. So here it would be a divided by s. First part is easy because we know that there is no same as we have done in previous case. But if you remember the previous case when we were having repeated roots, we were putting an s sign on the top, right? Okay, so in this case it would be bs plus c divided by s square plus 4s plus 104. In case of repeated root, what we were doing, we were writing it a divided by s square plus 1, s plus 1 whole square, then plus b divided by s plus 1, and then c. We keep on decreasing the root. But in this case, since we have complex roots, so if you have any complex root in this case, we'll be writing on top as bs plus c. This is how we write the partial fraction when we have complex roots. Okay, now the next thing is same as we have done in previous step, is s divided by s square plus 4s plus 104. So now we have this equation and we want to find a and b. So we just need to cross multiply it. So it would be 2s plus 104 equal to a into s square plus 4s plus 104 plus bs plus c into s. Now from here onwards it's same as the previous case. We just need to solve this equation. We need to separate s powers and then we need to compare it on the other side. So it would be 2s plus 104 equal to a s square plus 4as plus 104a plus b s square plus cs. So we can write it as 2s plus 104 equal to a plus b, and in this case, so we need s square together, then 4a plus c into s plus 104. Which means that we have split our equation in terms of s powers, decreasing s powers. So it means that from here we can easily find our constants. How? So it means that constant would be compared with constant. So it means a 104 equals to 104. So a would turn out as 1. So a is 1 because we compared only the constant parts. Then we are going to compare the s term. So we know that if we compare s terms, so 2 would be equal to 4a plus c. And we already know a is 1 plus c, so c would turn out as minus 2. And now finally we have the s square part. So we know that a plus b equals to 0 because this thing on this side is 0. A we already know is 1, so we get to know that b is equal to minus 1. So it means that the very first part was to find the, same as previous cases, find the partial fraction.
How do you know that a plus b is 0?
Because we are just comparing the two sides.
Okay.
So on this side you can see that we have s and we have 104. So I can write this as 0 times s square. It will not affect the equation, right? So that's why we compare 0. So So when there is no power here, we compare it to 0. So here S is accompanied by 2, so that's why this part would be equal to this part. So this is how, if there was no S on this side,
Yeah.
then it was equal to 0,
Right.
right? So it means that now we have A, B, and C. So it means that we can write this equation as one divided by S, because A was 1. B was B was minus 4S. C is also minus 2, right? Okay, so it means that we have 1 by S minus S plus 2 divided by S squared plus 4S plus 1 2. Now we need to take inverse Laplace, right? We just split them. Now taking inverse Laplace transform, we'll see that how we're going to do it. For this part, we know. What is inverse Laplace for this part? 1, right? 1 or U of t. That's good. And what would be the Laplace transform for the other part? So for this part, we know that inverse Laplace transform is 1, or sometimes we also write U of t, because we know that Laplace transform is for 0 to infinity. So even if we write 1, even if we write U of t, that doesn't matter, right? Because if you want to find Laplace transform for 1, Laplace is from 0 to infinity. If you want to find for U of t, it's also from 0 to infinity. So if you write 1 or U of t, that doesn't matter. So if, for example, you, in case if you get an exam, something, a function multiplied by U of t, so you know that it's same function. Yeah. Okay. So now finding for this part is slightly trickier. How are we going to do this,
Can we
sir?
split it so it's S plus 2 equals to plus 1 and 2?
This one,
Yeah.
the denominator, right? Yes, we have to do something like that, because the only thing at the moment we know something like this, S divided by S square plus omega square, or we know omega divided by S square plus omega square, right? We only know these two things for which we already know that what is our Laplace transform, right? So it means that we need to do something with it. It means that when we have S, we know this is for cos, and when we have this, we know this is for sin. Okay. So it means that we have to somehow play with this. But now you can see here that looking at this, I can see I could get a shape like this. Why? Because we have S on top. And if we say that, if we have e power minus at cos of omega t, for this I know it's just shift S by a, S plus a This is how we do, right? We know that for cos, Laplace transform is this. If we shift it by e power at, we just replace s divided s plus a, replace s by s plus a. So it means that here I can do something, I can split this and transform it to cos. So how are we going to do that? I can put it in the same box. Okay, so it means that we have to somehow split this, right? How are we going to do that? Okay, we have s plus 2 divided by s square plus 4s. If I write it as 4 plus 100, it's still the same, right? Then if I move further, I write it s square plus 2 into 2s plus 2 square plus 100. True? It means that now, what is this? This is formula for s plus 2 whole square. So it would be s plus 2 divided by s plus 2 whole square. And also I know that we have, for 100 I can write it as 10 square, right? So it means that now I know what this looks like. So what would be inverse Laplace transform for this part? I know this is cos, right? I know, one thing I know is cos. One thing I know is cos of 10t, cos of omega t, 10t, and omega is this term, right? So which is 10t. What else with this?
E
E power, yes?
minus 2.
Yes, e power minus 2t, right? So it means that this is how we look at it and then we decide what we should do with it. If, for example, there was no s on the top, then we need to think of something different, what we need to do. But at the moment, you can see that it's s plus 2, so so if we write inverse Laplace transform for this function, so finally inverse Laplace is equals to, for this, as I said, I can write u of t or I can write 1, doesn't matter. And minus, for this part it would be e power minus cos of 10t. And since, as I said, Laplace is always for t greater than or equal to 0, so that's why I said if I write it u of t or if I write it 1, that doesn't matter, it's the same thing. Okay. So it means that this is how we find Laplace when we have complex roots. Any question on this? So in your phase test, one of the question would be from inverse Laplace transform. It can be distinct root, repeated root, or complex root, right? And then
How many equations will there be?
2. I guess 2, yes.
One Fourier and one Laplace?
Sorry?
One
Hopefully, yes. One from Fourier and one from Laplace. I also prepared your final exam already.
Are you going to give us a question then?
Yeah, I will give you the whole exam.
Thank you. Appreciate that.
Is there any assignment in this module?
Yep.
It says on the fairly.
Assignment supposed to be the first.
Yeah, so assignment
The first test is this.
/phase
Oh,
test. So.
thank you.
Okay.
Thanks.
Is it
Okay, so this was just a plot for this, which you can see that finally we came to know that this was the inverse Laplace transform. And if I somehow plot it for different values of omega, for example, you can see in this case omega is 10, which was the actual example, and the same MATLAB code, you know how to plot it, so you will get something like this. So it means that we were having a function, a system which we solved from somewhere, although we directly received a transfer function f of s, but if we solve it, which we'll do later, then we can analyze it in time and we can see that what it looks like. Then there is another example. I'm not going to solve it, but just to show you something, I could solve the final steps because this is slightly different, which I want to introduce. You can see again, you have f of s, and then you have a denominator. Again, in this case, you can see that the denominator is same. The only thing different than this question and the previous question is, in this previous question, you can see that your numerator was slightly different. So, okay, so if, for example, we solve it using the same partial fraction, which we already know, you will finally get something like this. 1 by s minus s plus 22 divided by s square plus 4s plus 104. For this part, again, as I said, that we know what is Laplace transform, right? Inverse Laplace transform, which is 1 or u of t. However, this part we need to solve. What is this part? This part is s plus 22.
I think it's all similar one.
Slightly different.
That's the same way.
Okay.
It's going to do with the cos, right?
Now, in this case, we will be having cos and sine together. Because in the previous case, you can see that you were having s plus 2 on the top, and luckily in the bottom we tried to do something, and this s plus 2 and this was same, so that's why we came to know that it's e power something, right? But in this case, if you have a look on it, if I solve it, I know the denominator from the previous step, which is s plus 2 whole square plus 10 square, right? S plus 22. This we already solved in the previous step, right? But in this case, the difference is I don't have the same shift here which was in the previous case. So I need to do something with it. So it means that I need to split it further. How are we going to do that? It means that I can write it as s plus 2 plus 20. Right? So what we have done, we have split it. Then again we can split it. It would be s plus 2 divided by s plus 2 whole square plus 10 square, and I can 20 divided by s plus 2 whole square plus 10 square, right? I can split it. And from here I can see that I am somehow getting sine and cos both, right? For this part, it is very easy. As in the previous step, it is cos 10 of t with e power minus 2t. However, for this part, right, for this part would be sine. But what is but here? But is we don't have same omega on the top, right? The top should be 10. Yeah, we can just split it like 2 times 10. So it means that this part I can simply write it as 2 times 10. So it means that now we have omega divided by s square plus omega square. So I can simply write inverse Laplace transform would be equals to e power minus 2t cosine of 10t minus, okay, and then here you have 2 times sine of 10. Okay, so it means that now, that's why you see that we solved it in such a way that we get finally in this form, and then if I finally put it in this equation, I will get the same answer. So here the only trickier part was that we need to make our function in such a way that it looks like the it looks like transform for a known function, so that we can find inverse Laplace transform. Is it clear, right? So this is a table which probably I will provide in the end of your exam sheet. You will see this table which is for Laplace transform and inverse Laplace transform. Okay, now we are moving towards last part of AI, and then we are finished, but this part is the important part. Okay, so from this part we're going to see how we find transfer function for a system. It means that if, for example, I say that I'm giving certain input to a system and I'm getting certain output, so what is that system? So we need to know that how that system behaves, and how we're going to find the transfer function, and then we'll move ahead with some other things as well. So here you can see that we have a system, we have input and output. If I want to write it in time domain, it would be x of t is input and y of t is output, right? And if, for example, I take Laplace transform of this x of t, which we know it would be x of s, similarly y of t would be y of s. As I said, that Laplace transform is a tool to solve something with more ease, and we'll see that. So it means that if I provide x of t, it would give me y of t. Similarly, if I see it in Laplace domain, if input is x of s, y would be output would be y of s. Now, when we talk about system response, we have two things about it. What we have two things. One is if for example, we take an example of a battery. So I'm giving an input to the battery and it will charge, right?
Yeah.
But depending on how much was the initial charge, it will behave slightly different. If, for example, the battery was fully discharged, it means that it will be charged from 0 to some value. However, if it was charged at a certain point and I started after that point, it means that input plus that initial value would impact. So that's why we say that we have, for any system, we have two types of responses. One is called zero state response and one is called zero input response. How the two are different? This zero state means when the battery was fully discharged, there was nothing in the battery. It means that only input was affecting the system. However, in the second case, if, for example, there is no input, only we see that what was the initial charge of the battery, how it behaved. So it means that we have two things. In the first case, state is zero, means there is nothing in the system at time when we started. At time t equals to 0, there was nothing stored in the system. So it means that at time t equals to 0, output of system was 0. It means that there was nothing in the system. So this thing is called zero state response. Now the second thing is when we don't have input, when the input is 0, and at that point whatever we get would be zero input response. And any system, like I said, that if, for example, you consider battery was a discharge and you apply input, and in the second case you consider that battery was at some point and you are applying input. So it means that if I split them separately, what I can do, I can find a response for the system when there was no initial state and only the input, and then I can also find a response where there is no input and only state. And if I combine both of them, I will get the total response, that this was under zero state, only input, the second was only state and no input, and combinedly it will tell me that okay, when you applied input, there was an initial state, so instead of starting from 0, it was starting from certain point. So that's why whenever we talk about any system, we see that how that system behaves. Okay, if for example I am pushing this test, so I am just applying input. There is no initial charge or anything in the system. But we do have some system which have initial charge, and battery is very good example. Now we'll move forward and we'll see how we going to find a transfer function. As I said, capacitor was a very good example. So what is zero state? Zero state is at time t equals to 0, when you applied input, there was no output. It means that output was 0. However, in the second case, you can see that there is no battery. There is nothing at the input. There is nothing applied from the input. At that point, whatever would be the output would be 0 input response. And these two responses are very important to consider. Another important thing is how we find transfer function? For any system, we will start for one system afterwards. For any system, if we have differential equation, because any system is represented by a differential equation using derivatives. If we take that system, if we apply Laplace transform, we can get transfer function. But if you remember, when we said Laplace transform of f prime of t was f of s minus f of 0. If you remember that, when we find Laplace transform for a derivative, it means that s into Laplace transform of the original function minus f of 0, which was time function at time t equals to 0. So it means that in this case, you can see that you have f of s and also you have function value at time t equals 0, which is indirectly an initial state. So it means that when we're going to find transfer function, we will assume that there is no initial charge or there is nothing in the system. So to find a transfer function, we will apply Laplace transform, but you remember this was an initial condition, as I explained that. What this f of 0 says, it says that value of function at time t equal to 0. But to find Laplace, to find transfer function, we will consider this condition, where we say that there is no state, there is 0 state at that point. Okay. So that's why we say that transfer function of system is generated from the Laplace transform of differential equation that models the dynamic of system, assuming all initial conditions are 0. It means that transfer function could be found using 0 state response. Right. So let's solve transfer function and an RC circuit using Laplace. In the exam, if for example you are here, you will see that we will start with RC circuit. So we know that this is a resistor. If this is V1 of t, this is resistor, this is capacitor, and this is I, and voltage across capacitor is V2 of t. If in the exam you will get something where you are going to find system response, probably you will get a differential equation already and you will be asked to find the transfer function or do anything. But overall, the idea would remain the same. Okay. Now here, as I said, that transfer function. So transfer function is always between input and output. Here, what is our input? Input is something from this side, which is probably a DC voltage, and output is voltage across capacitor. So we want to see that what happens to voltage across capacitor when we apply certain input, and we want to see the output. So we want to find the transfer function. So it means that here interest is at input, which is this one, and this one, which is output. So it means that we want to see a relationship between input and output. Okay. Now, when we want to find relationship for a circuit, electrical circuit, what we do, we use circuit analysis. We use voltage law or current law, which is simple, that start from one end and go towards the other end. So it means that input is equals to whatever you apply here is equals to voltage drop here plus voltage here, right? This is basic circuit analysis. Whatever you apply input, it will go across resistor. So voltage across resistor plus voltage across capacitor, which we denoted as V2. We said this is. Now we know that VR is I times R and V2 T. Our main objective is to find transfer function. And what is transfer function? Transfer function is V2 of S by V1 of S. It means that input and output, relationship between input and output. We will see later as well transfer function. Okay. Now, at the moment, we don't have a differential equation, and because we want something between voltages, so we want this circuit to be all voltages. At the moment, this current is making problem for us because it will not let us solve our system. But something we know is the current which will flow in this circuit, we know that current. So if you have a circuit with a capacitor, this is very typical formula for a capacitor, that rate of change of voltage across capacitor multiplied by its capacitor would give you the current. So since it is a series circuit, so whatever current is flowing through capacitor, the same current will flow through resistor as well. So that's why we will write V1 of t equals to C dV2 by dt plus, and here is R as well, plus V2 of t. Now you can see that we are getting closer, because we have V1, V2 and V2. So it means that now our system is in voltages. Now we can apply Laplace transform, right? So let's apply Laplace transform. So apply Laplace transform, assuming all initial conditions are 0. Initial conditions are 0. What does it mean? It means that there was no voltage across capacitor when, so it means that voltage across capacitor at t equals to 0 is 0. It means that voltage across capacitor at t equals to 0 is 0. Because this is what we said, that we will assume when we're going to find transfer function, we will consider that the initial conditions are 0. And why do we need that? Because we know that when we apply Laplace transform, we will need initial conditions. Okay. So I will remind you again, if you have f of t and the Laplace is f of s, so Laplace transform of f prime of t is s times f of s minus f of t equals to 0. This is Laplace transform for a derivative, right? Okay. Now apply it here. So it would be v1 of s equals to cr times. Now we have a derivative for v2, right? So what would be Laplace transform for this? Same as here. So what would be Laplace transform? So here you know that this is df of t by dt, right? So this is equivalent to this. So this was the Laplace transform. So what would be Laplace transform here? I will leave it here and I can write it this one. I know that for v2 the Laplace transform is like I said in the previous case, that if you have x of t is input, y of t is output, right? If you want to see in the Laplace transform frame, it would be x of s input and y of s output. So similarly here v1 of t is input, so its Laplace transform is v1 of s, v2 of t is output, so its Laplace transform is v2 of s. Now this is transform for the derivative of v2. So what would it be? What would it be?
If you go into D,
No, we can use directly this formula, right? So it means that s f of s, whatever is here, s times its Laplace transform. So you can see that here s times v2 of s, right? Minus v small v2 of t equals to 0, right? Mean function, small v, I mean function of time, just to differentiate, right? Okay. But as I said that transfer, so you can see that in here, what I want to find, I want to do something like this. If I don't have this term, I can simply take common and I can split, I can rearrange them. But if I have this term, I can never rearrange them. So that's why we say that when we want to find transfer function, we say that the initial conditions are 0. It means that we are considering 0 state response. Okay. So it means that v2 at t equals to 0 is equals to 0. So we can write it as v1 of s equals to c times r and s v2 of s plus v2 of s. It means that initial condition, we have put initial condition as 0. Finally, I can take CRS plus 1 into V2 of S, and on this side is V1 of S. I can bring it here, so it would be, I need to find, what I need to find, transfer function is always output by input. So we want to find V2 of S divided by V1 of S, so it would be 1 divided by CR plus CRS plus 1. And normally, as I said, that whenever we write Laplace transform, then we also go back to time domain. So it's always important to make your function look like a known transform. So I can write it as 1 divided by, I can take CR common, inside it would be 1 plus RC, right? This is what I can do, okay? So it means that this is your transfer function for an RC circuit. So it means that if, for example, here you can see that you are having a differential equation which we wrote from the circuit, and maybe in exam you need to write it from circuit, but it is also possible that you get this differential equation directly, and you just need to apply Laplace transform by assuming zero initial conditions if you are asked to find transfer function, and you get a transfer function. So it means that I have V2 of S by V1 of S, and this gives me a transfer function. And we always say that transfer function is calculated by saying that we are calculating zero state response. Why? Because the initial state in initial condition, where was your system at time t equals to 0? We always assume that the state was 0. Clear so far? Right? Okay. Now, it means that we have this transfer function. So it means that if I draw this box, it was x of t, y of t, x of s, y of s. So I know that this is, if I don't know at the moment what was the system in time domain, I can say simply that from here I can say that if this is h of s, so in this case h of s is, if I say this was v1 of s and this was v2 of s. So h of s is relating v1 and v2. What does it mean? It means that v2 equals to v1 h of s. So I can write this as a transfer function, right? So it means that if I want to find v2, I can simply multiply v1 with this and I can get output. So it means that transfer function is telling me what is happening to your input towards output, right? When you apply certain input, you get certain output. So it means that transfer function is very useful, right? Now, we will move ahead a little bit further. Okay, so this was zero state. So whatever we calculated, transfer function, we calculated it with zero state, right? With zero state, but we have certain input. What if we assume that the input V1 of t was a unit step? If we assume that the input to the system was a unit step, what would happen to the output, right? One way was that I used the same mathematical model, provide a certain input in time domain and solve it, right? This was one method, but that method is not easy method. Here we can do something. So we already know transfer function, which was from zero state. It means that there is no state. And if someone asks me to find zero state response to a step input, so it means that what would happen to the circuit if the input was step, right? So it means that now I can easily do that. Why? Because I know what is this box. I know this box is h of s. I know if x of s is this, y of s is this, and y of s would be equal to x of s times h of s. I know from here now, right? I have this box which I know is transfer function. I know if input comes to this, it will be multiplied with the input and I will get an output. So it means that using transfer function, using input, I can find the output. So if when someone say that find zero state response to a step input, it means that the input is unit step. And everyone know, if V1 of t was unit step, what is V1 of s? If input was unit step, what is its Laplace transform?
1.
1 over s. For unit step, the Laplace transform is 1 over s. Very simple. So it means that if someone told me to find zero state response to a step input, overall he's asking me to find the what is happening in time domain. But I cannot solve easily in time domain. So the best thing was to take this transfer function, multiply it with a step, and then take inverse Laplace transform, right? Simple. Okay, so it means that I need to find V2 of s, which was h of s times V1 of s, output equals to transfer function times the input. So it means that h of s here is why I have written in this form. I can take CR, it's the same thing, but it's known form of that. Okay. And I need to apply it with input. Input in this case was 1 by s, right? So it means that now I have to solve it. And we know how to solve it. We know that we need to split it. Whenever you are said that find response, it means that you're always talking about time domain, but you're just taking help from Laplace domain and finding the time domain functions. Okay. So, right. So it means that I need to solve this, which is 1 by RC s into s plus 1 by RC. So it means that this is a partial fraction, right? If I write it in the form of A divided by S plus B divided by S plus 1 by RC, if I know A, if I know B, I know what is system response, right? If I know A and B, I can say this is 1, whatever is A, and this is e power minus t by RC, right? So it means that I can get a time domain function from this. And this would be zero state response to a step input. If, for example, you are given a differential equation and you are being asked to find zero state response to maybe something else, so you are able to find it. And how are you going to do that? The very first step would be to write transfer function. The next step would be whatever you are asked, take that corresponding input, find its Laplace transform, put it in this equation, then finally take inverse Laplace transform, right? So it means that whenever you are asked to find zero state response to certain thing, you have to take that input, and that would be a very known input. You would easily know what is Laplace transform. So it means that for this, I can easily solve partial fraction. I can find A, and I can also find B. I will write final equation because Okay, there is one small thing that I missed. It is unit step, but it has certain amplitude. So that amplitude is V. So it's that it's instead of 1, it has certain amplitude. So this is unit step, right? We know that this is 0 and is go to certain value. So the thing I saw, it was for 1, but I want to generalize it so it's V. It has any magnitude, any V, right? So it means that instead of here it is V by S, V by RC, and finally it means that when we're going to solve it, we will get it in terms of V. Okay. So it means that if I want to find V2, so V2 of t is the inverse Laplace transform of this function. Considering that we know what is the value of A and we know what is the value of B. Okay, I will just write directly. Equation is V okay, so it means that the value for A and B was simply V. So from here I can say that the value of A was minus V by VRC. If I put A was V, and similarly B was minus V. So that's why finally you get this equation, but we can solve it. I don't want to waste time on that. But okay, so it means that now we came to know that this is response for when you have a step input. So if it means that if you apply the step input to capacitor, this is how the response will look like. It means that if I draw it here, it means that we apply V response to a capacitor, and if I want to see what happened to V2 of t, so let's see. So this is time. So it means that if I put t equals to 0, e power 0 is 1, 1 minus 1. So it will start from 0, it will slowly rise, and if I put t equals to infinity, e power minus infinity would be 0. So the maximum value that it would reach would be V. So it means that it would start from 0 and will go up to V. So and this is we get from the its time domain function. But how we found it? We found it by simple application of Laplace, and we have done so many times. Laplace transform and inverse Laplace transform. If I show you here, so it means that this was your RC circuit, and finally we came to know that if we have a step input, so zero state response of first order circuit was step input. So the input was step, and what was the step? It was V by S, so step was V. So you can see that it started with a certain point and it will reach to the maximum value to which the step is applied. So if the step was 1, so the maximum point it can reach would be 1. It means that you applied a 1 volt signal here, capacitor will take some time and then it will reach maximum to the 1. So it means that whatever input you have applied, the output will reach to that maximum level. And there is another thing that we sometimes say is when your value reaches to 63%, this time is called tau. This time is basically called time constant, and this we represent as tau equals to RC. And this is time at which we reach 63% of final value. This time is called tau. Okay, so it means that this was zero state response to a step input. Now the next thing is we're going to find zero input response. So it means that we have zero state response, we have zero input response, then we have the overall response, right? Okay. Okay, now we're going to apply zero input response, so it means that this is R, this is I. Right. So it means that in this case, input is zero. Consider that we applied input in the previous case, we charge our batteries to a certain point, and then we remove the battery. Then we remove the input. So it means that now the battery will discharge, right? If we talk about electric vehicle, we charge it and then. So it means that we charge it and now we are starting from a point, which again we can say is we are starting at t equals to 0, but at this point V2 of 0 is not equal to 0. Previous case you were saying that the charge on the capacitor is 0, but now we say that we charge our battery at night when in the morning, at any time we started, we considered that time equals to 0, there was some charge on the capacitor. So it means that now the initial value on the capacitor or on the circuit is not 0, right? So it means that if you want to see again in this case, we have V1 of t is equals to 0 and V2 of t has some value which we need to find. But we also know that V2 at t equals to 0 was certain thing if I say this is V2 of 0. I say it's just some value. I don't know at the moment, but it is certain value. Okay. Now let's solve it again, which is very easy. So starting from this, I can say that 0 equals to IR because input is 0 would be V2 of t. Same as previous case, instead of this, it is 0, right? If I go further, I know it's I is equal to C dV2 by dt. So I can write CR dV2 by dt plus V2. Okay, now the next step is what we're going to do. We're going to apply Laplace transform, right? Okay. Apply Laplace transform, so 0 CR. Here Laplace transform would be S. What would be Laplace transform?
Cosecant happens.
What is Laplace transform for a derivative?
S V2
S V2 of S, right? Minus V2 at time equals to 0, right? Plus V2 of S. You remember when we were finding transfer function, we said we always transfer function is fine by assuming initial condition 0. Why? Because there is 0 state response, but in this case this is not 0 state. In this case it has some value, right? So we say that CRS V2 of S minus CR V2. I know, I just said that value of V2 at time t equals 0 is some value. I don't know. It can be any constant number, right? It can be any constant number. It can be, if for example my battery was charged to maximum value, it would be that. If I consider that in the previous example, I left at that point and started from that point, it means that the initial condition was V, which was maximum charge. Okay, now we can CRS plus 1 V2 of S minus CR V2 of 0. I just combine the V2 of S because my main objective is to find V2 of S. So if I take it on the other side, V2 of S CRS plus 1 equals to CR V2 of 0, right? If I take it here, so it would be V2 of S because my main objective is to find somehow V2 of t. So that's why I am trying to rearrange it. CR V2 of 0 by CR plus 1. And finally, I want to convert it into a known form, so it would be V2 of 0 CR into S plus 1 by CR. So CR will be cancelled with CR, so finally you get V2 of 0 by 1 plus. So now we know what is inverse Laplace transform, right? What is inverse Laplace transform for this one? What is the inverse Laplace transform?
Cover circles.
No, this is 1s plus something, right? This is just s. There is no square that we convert to cos or sine. So it's just, what is Laplace inverse for this? V2 of t equals to V2 of 0, which is constant. It doesn't matter, on top is constant. What would be inverse Laplace transform for this part? This is s plus a, right? 1 by RC, the constant value. So what would be that? Anyone? Yes, e to the power minus t by RC, right? So it means that now you see there is no input in this case. So it means that if I want to plot this, if I want to see how it looks like, I can see that at time t equals to 0, e power 0 is 1, right? At time t equals to 0, v2 equals to 0 is, this term would be 1, it will start v2 0. So it will start from that constant point, which was the initial condition actually, right? And by time, if I put t equals to infinity, this term would be 0. So it means that it will go down to a certain point. So it means that the capacitor was charged to a certain level, and after we remove the input, it makes sense that it will discharge. And why choosing this circuit? Because it's more easy to visualize and understand this circuit, because we all know about batteries. So this is how we take the zero state and zero input response. Let's say if it was discharged until this point and I applied an input, so it will go again on top, right? So that's why we say that the total response is combination of this plus the actual response, which I will go here. So it means that, as I said, it will start from that initial value. If someone is confusing with V2 at t equals to 0 equals to V2 0, you can say that it is certain value of V. So instead of this, you can write it starting from certain value, whatever that value was, okay? Okay, now he said that complete response for the system is equal to 0 input response plus 0 state response. 0 input response we just calculated, which is this one, and 0 state response is this one. So it means that if, for example, there was no initial state, if we say this was our overall response, and consider that there was no initial charge in the system, this term will go to 0, right? And only this term will hold. So it means that this is a complete response for a system where we consider input as well as we consider the zero state. One important thing is this zero state response will stay same whatever, right? Because there is nothing that we can change. Mean the input is 0, same R, same C, except what is the initial condition. But the other response that we have calculated, zero state response that we have calculated, this was to step input. It means that in this specific case, the input was a step. If, for example, this was a ramp, or if this was some other function. So at the moment we have said that the input, which is V1 of t, was u of t, unit step, right? That's why we say that V1 of s is 1 by s. So that's why on top you can see that zero state response to step input. But what if the input was a ramp? For a ramp, the function is this one, right? For a ramp, function is like t. So what would be input now? What would be input? What would be Laplace transform for t? What would be Laplace transform for t?
It's gonna be about
No?
1 over s.
1 over s square, right? So it means that now instead of v by s, it would be v by s square. So it means that overall your inverse Laplace transform would be different, right? If, for example, someone say that v1 of t was delta of t, which is impulse response. If, for example, someone said that how your system would behave if we apply an impulse and then finish. So what would be input in this case? What would be V1 of S? What is the Laplace transform for impulse? What was Fourier transform for impulse?
1.
1. What is Laplace transform for impulse? 1. Right? So it means that in this case this would be 1. So it means that depending on your input, your zero state response changes. So it means that depending on your input, your output changes. This is what we know, right? This makes sense because if this is input and this is output and this is transfer function, so it means that y of s is equal to x of s times h of s. So whenever the input would change, your response would change. But which response? Only your zero state response, right? Whereas your zero input response is almost the same. The only thing is that this term might change depending on what value a certain thing is charged or something. Okay, that means that overall your response look like this. But one important thing you can see here, if we, like I said, if your system was to some initial condition and if you're also applying an input, then it will start from that point to go on. But if, for example, your input is 0, this part would be 0, only this part would be valid and this circuit would be valid. So it means that overall this is correct. This equation is true, whatever condition you take. If you say you have initial condition, you have input, then this circuit, this thing would have a hold. So it means that when no state, only this part would hold and the graph will look like this one, starting from 0. When we say that there was no input, only initial condition, your graph will start from certain point and go down. Imagine like a water tank that you are just using it, you are not filling it. But consider that your water tank was at half and you are also filling it. So it means that your water tank was at a certain condition and you are still filling it. So it means that this equation overall holds. So that's why we say something from here you can see now is if I see this equation, so I have V, which is a maximum point, right? Vf2 of 0 is the initial condition. So I can say that overall response is normally start from 0, which is the initial condition, go to infinite, and there is also a midpoint, which I said when we reach to 63% of the chart, which was this point. So if we say that it start from 0 or any initial condition, it go to 63% and then it go to infinity. So this is how we generalize that a step response generally looks like it start from initial condition, then reach to 63% of final value and then reach to infinity. This is how we say that a step response for any system looks like. But if it was something different, impulse, so this case it would be impulse response. This case was step response, which we already calculated, and this last case is ramp response. If, for example, your input was sinusoid, then it would be sinusoidal response, and so on. Okay, there is another question that I am going to solve in the tutorial class because I have to cover one last important bit. And then we are finished. Okay.
What is the covenant?
Sorry?
Which the two of them? Covenant. Laplace transforms?
Yes, Laplace transform and yeah, overall Laplace transform, yes. So we just said that if we have x of s and if we have y of s, we can say that y of s is equals to x of s into h of s. This we know in frequency domain, right? This means that if we have something in Laplace, then now we'll move towards, but at the moment what we don't know one thing, which is that x of t, y of t, what is y of t as x of t. We don't know at the moment, right? That's why we use the help from a Laplace transform, right? But now we will move to a point, we will see that what is this. This brings us to a concept which is called convolution. Convolution. What is convolution in general? If I look at here, I can see if input is x of s, output is y of s, and if I want to find y of s, it would be x of s into h of s, right? True? For this h of s, there should be some h of t as well. But we don't know, like here we know that y of s equals to x of s multiplied by h of s. But here, for this system, h of s, there should be some h of t if we take inverse Laplace transform, right? But we don't know what is this relation. So I will go later on. We don't say that if you have an input time function and if your system was also a time function, so how these two decide the output. So if two time functions, so if I want to see that how one time function is affecting another time function, I cannot simply multiply them. I have to find output by convolution. So it means that if you have an input which is a time function, if you have another system which is also a time function, if you want to find output, you have to convolve them. And how do we find convolution? We will see it now. So normally convolution is if your function f1 of t convolution f2 of t is equals to f1 of tau minus, multiply by f2 of t minus tau. So it means that this is how we find convolution. And now you will also see, I will move in a bit, you will see the significance of Laplace transform. Because apparently you see that this looks difficult, right? Even from looking at it, we can say that this is something which is difficult to solve. So it means that we want to find a way to solve it. We have one way, Laplace transform, right? So it means that why convolution was important, because we want to see that how time domain functions affect each other. And of course, if for example I have any system, I am giving input, I am taking output, that function would be something. At the moment we don't know what is that function, but we know that x of s, h of s, y of s. So let's apply Laplace transform on both sides. So if we apply Laplace transform, so it would be f1 of t convolution f2 of t. Here it would be 0 to infinity, function is this whole thing, minus infinity to infinity, f1 of tau minus, f2 of t minus tau, d tau, e power minus st dt. This is how we find Laplace transform, right? We just take the function and we find the okay. So it means that in order to solve convolution, we want to take help from Laplace transform. If you apply Laplace transform on both sides, this is what we get. And now we have to solve it. You see that this is integral of time. In this there is no t. This is tau. This is something different. Although this was originally time, but when we were finding convolution, we replaced it with tau. So it means that this Laplace will not apply on tau. It will apply on this function only, which has t. So we can take the other function out. So I will write it as minus infinity to infinity. I will take it back because this is all tau things. F of tau d tau, and inside I can write 0 to infinity f2 of t minus tau e power minus st dt. This is how I can write it. That means that this tau was not function, means this integral is on time, means Laplace is on time, not on tau. It means that I can take tau outside. So far I have this one. Okay, if you remember, we solved, we had a time shift, that if you have shift in the time, and if you want to find Laplace transform, you can do that. Okay, so to solve this, I can say lambda equals to t minus tau. So d lambda would be dt and t equals to lambda plus tau. So I actually want to solve this part. And to solve this part, I am actually trying to transform it. Okay, so I can write it as f2 of lambda e power minus s. This would be lambda plus tau, and this would be d lambda, and this limit. Now if we look at this limit, this starts from 0 to infinity, right? And this limit was originally on t. So if I put t equals to 0 in this equation, lambda would start from minus tau. So it means that this is from minus tau to infinity. And we also have this on the back, minus infinity to infinity, f of tau d tau. So there is one last step now, and then you will get the you don't need to worry about this derivation, because these derivations are just to make sense for you that something is correct. Okay, if I take it here, so it would be minus infinity to infinity f of tau d tau. Inside it would be minus tau to infinity. This thing is f of lambda. I can break this minus lambda and e power minus s tau d lambda. I can further write it as minus infinity to infinity f of tau. I simply, what I have done, I have splitted these two terms. It would be e power minus s lambda s tau d tau, and also you have minus tau to infinity f of lambda e power minus s lambda d lambda. What I have done here, I have simply f of tau d tau, I took this and combined with this part, and secondly I am left with this part. Now you can see that if I somehow ignore these limits, instead of minus infinity if I say 0, instead of minus tau if I say 0, what this looks like? What this looks like? Any known integral?
Fourier series?
Laplace transform. This is Laplace transform, right? It means that here the Laplace transform is for f of tau, and here it's Laplace transform for f of lambda.
It's multiple now, right?
So yes, they are multiplying. Sorry, it was f1. So this is f1, and this is f2.
I have a question. Why do you assume to be 0?
Yes, because we apply Laplace transform, right? And we already know Laplace transform don't exist for negative number. It exists from 0 to outside. So that's why instead of taking minus infinity, I took it 0. Instead of minus tau, it's 0. Because tau is a positive number and Laplace transform holds for. So it means that from here, we came to know it's f1 of s times f2 of s, right? It's just Laplace transform of f1 of s, f2 of s, right? So it means that convolution in time domain, if we can say that convolution in time domain is multiplication in frequency domain. It means that if I write f1 of t convolution f2 of t, in Laplace domain, they are f1 of s, f2 of s. So it means that if you want to find convolution of something, you don't need to solve this hectic integral. What you can do, you can simply find Laplace transform, multiply it, and then take inverse Laplace transform, right? It would be the same. So it means that if I take inverse Laplace transform of f1 of s times f2 of s, this will give me f1 of t convolution f2 of t, right? So it means that that's why we say that convolution is very important property. Don't worry about these integrals, you don't need to solve it. The only thing that you need to remember, and the idea was to prove it so that you understand it, that if a system is convolution in time domain, it is multiplication in the Laplace domain. This was an important point. Okay. Let's solve one example so that we know what we meant by this. So you have f1 of t and you have to find convolution for t greater than equal to 0. Normally convolution, as I said, is the main application is to find how systems behave in time domain. Like I said, if there is one system in time and if I'm applying it to another system, how they. So normally we see systems not in negative time. We always see system in positive time. For example, if this is time is 0, I look after that what happens to that system. So always these things are for t greater than 0. So here the thing is that we need to find f1, f2 using convolution, direct method. Direct method means using integral, and part B is using Laplace. So here the main objective is to find convolution of these functions using Laplace, and then also, so if for example you have something in exam, so you should know that if for example you are asked to find using direct method, it means you need to solve integral, and if it is said indirect method, you need to solve it with Laplace transform. And like I said, here I written f t greater than 0, right? So I could have written e power minus 3t u of t. I don't need to mention then t greater than 0, right? Because I know that unit step is for t greater than 0. So it means that if I don't want to write it here, I can write this. So it's the same thing, that it's from 0 to infinity. Okay. Now let's see what is formula for convolution. So I know that formula for convolution is minus infinity f1 of tau, f2 of t minus tau d tau, right? In this case, as I said, that normally convolution is to study systems. So systems are for t greater than 0. But this limit, you can see that it's from minus infinity to infinity, which is not true, right? We need to do something. So it means that we'll see what we're going to do now. So it means that f1 of tau So if I say that t greater than equal to 0, so it means that if I talk about this, so t is in this equation, as I said, t is greater than equal to 0. So it means that this t is greater than equal to 0, right? In here, I mean tau is greater than equal to 0, right? So it means that for f1 of t, I can say that now f1 of t is replaced with f1 of tau. So here if t was greater than equal to 0, here tau would be greater than equal to 0. So it means that this is not true. This would be 0. This can not be negative, right? So it means that I can change this limit to a new limit which is 0. This is one part. Now the second thing. So I know f2 of t was again greater than 0, right? For f2 as well. For f2, as I said, is u of t, or if I say t greater than 0 mean, and f2 t was greater than 0. But now this t is replaced by t minus tau. So what does it mean? It means that t minus tau is greater than 0. True? The same t is replaced, right? Again, this is I'm showing you just for your understanding, then I will tell you what you have to do if you have to solve your convolution directly. Okay. It means that t greater than tau, if I take tau on the other side, or I can say that tau is less than t. It means that tau is less than t. It means that it cannot be infinity. It means that tau is greater than 0, less than t. So I can say that this upper limit, so I can say that this upper limit would be t. So tau between 0 to t, right? Okay, so you don't need to, even if you don't understand, that's fine. If you are asked to find convolution, normally as I said, the convolution is for t greater than 0. You don't need to worry, you just need to write 0 to t, f1 of tau, f2 of t minus tau, d tau, okay? You just need to use this formula. You don't need to worry about all those things. Those were just for your understanding. And as I said, convolution is something which we apply on systems, so it is for t greater than 0. Okay. Who can find convolution using Laplace transform? So as we know that f1 of t, f2 of t, convolution in time domain is f2 of s, right? So if I find Laplace inverse of f1 of s, f2 of s, I can easily get convolution, right? So it means that I just take Laplace of first function, Laplace of second function, multiply them, right? And then take the inverse Laplace transform. You want to try? I should solve it. So the answer is I should solve it. Okay. So I know f1 of t is e power minus 3t. What is Laplace transform for f1 of s?
Just 5 units of t.
S? What is Laplace transform for e power minus 3t?
Yes, minus 3.
No, plus
Plus 3.
Okay, good. S plus 3. And if f2 of t? S plus 2, right? If I want to find f1 of s times f2 of s, it would be 1 divided by s plus 3, 1 divided by s plus 2. I can write it as a divided by s plus 3 plus b s plus 2. Right. So I can further solve it a into s plus 2 b into this. We have solved so many times. Okay. right? Now we can take s plus 2 equals to 0, which means that s equals to minus 2. I can get b into minus 2 plus 3, so b would be 1, right? B would be 1. And then second thing is s plus 3 equals to 0, s equals to minus 3, a into minus 3 plus 2, a equals to minus 1, right? It's mean that f1 of s times f2 of s, I can write it as minus 1 divided by s plus 3 plus 1 divided by s plus 2, right? This was converted into this. Now we know a and b, so I can say that. True? Okay, what is inverse Laplace transform for those two?
Well, it's just minus a to the power minus b. And
So if I take inverse Laplace transform, it would be minus
e to the power
e to the power,
50 minus 50
and here
e to the power minus 2.
t greater than equal to 0. Even if you don't write, that's fine. Okay. So it means that what is this now? This is convolution, right? Because inverse Laplace gives us convolution. So this is your convolution thing. So it means that it was very easy. Convolution in time domain is equals to multiplication in frequency domain. And this was indirect method where we solved it using now there is direct method. F1 convolution with F2 is 0 to t, F1 of t, F1 of tau, F2 of t minus tau, right? So I can put it as 0 to t. What is F1? F1 is 3, so it would be minus 3 tau. F2 is minus 2, it would be t minus tau, d, right? This is convolution. Okay. Now you can see that the integral is on tau, not on t. So I can somehow split them. 0 to t e power minus 3 tau, e power minus 2t, e power plus 2 tau, d tau.
After times the pallets, right?
Sorry.
Yeah.
Yes, so here it would be e power minus 2t I can take out. Inside it would be 0 to t. When bases are same power would be added, right? So minus 3 tau plus 2 tau d tau. And since integral was only on tau, so I took t outside. I come here, it would be e power minus 2t. So far good, right? And then finally we need to take integral e power minus 2t. Inside it would be e power minus tau divided by minus 1. And this is from 0 to t. Minus e power minus 2t. Upper limit e power minus t and lower limit is e power 0. So it will be minus 2t e power minus t minus 1. And now if I multiply it inside, it would be same as this one. So you can see minus e power, bases are same, so power would be added, minus 3t minus e power minus 2t. So it means that this thing holds. Okay? That means that convolution time domain is multiplication in frequency domain. So this gives us huge advantage, and in this case it looks good, it looks easy to solve because you have e power t, but if for example you have one e power t and other is sine function, then you have to go with integration by parts, so then it becomes difficult. So that's why it is important to use convolution, because convolution gives us an advantage.
Should be plus, isn't it?
Sorry?
Should be plus, isn't
Yeah,
it?
the second term, yes, second term is plus.
This part is not going to be
Sorry?
in the face.
So only the previous part until
Transform.
inverse Laplace transform. So in your phase test, you will be having one question from
Oh, yeah.
Fourier.
Is it
It
specific
can
one?
be Fourier series or Fourier transform. Right?
Is it for free series or free transfer?
Yeah. Okay. I will specify it.
No.
So you have one question would be from Fourier series, but only trigonometric Fourier series.
Oh, it's relative.
Oh, yes.
Right? Or Fourier transform. It can be Fourier series or Fourier transform, one question, and the second question is from inverse Laplace, right? Which is mean repeated root, distinct root, or complex root. So
It's three of them. One of them.
one of them will be. So I will give you two questions. So you will be having 1 hour to solve them, okay?
Gracias.
You just put that in.
So what are the topics for the Laplace transform?
Inverse. But the main exam is going to be from all topics.
Yeah.
Yes. By end of course I will.
Do you have any?
By end of course I will give you some hints off the camera. But yeah.
Good.
Yeah,
Turn off the camera. Camera is off.
You didn't record that, did you?
No, no.
I will definitely do
Take you out.
the region B,
Yeah.
which I will try to.
Prepare up.
Yeah. There you go.
It's a final game. So main question is something to be
Yeah, we can pass.
Too many things.
Not really fast.
For
This
the
one is not that hard. Much more than that one.
Yeah.
that's what we got, right? We got this.
Yeah.
Nice.
Each week
Oh yes. Oh, one more thing.
each week we will try to
Yeah, she asked a good question. She asked a question which is important, so everyone can listen. She asked a question that if in
Can you listen?
it's very useful the question she asked. So she asked that if we have a Fourier series and if we know that it is even or odd. So for example, it is even, so we somehow know that a naught and a n doesn't exist. So if you can somehow figure it out, and if you write the right reasoning, you can do that. You don't need to spend, for example, solve a naught and then it is 0. You can say that, okay, this is the reason and it is 0. If for example this is an odd function, you can say, okay, this is odd function and Bn is 0, you can do that, but you have to provide reasoning. If, for example, you directly write Bn equal to 0, you will not get marks, not in phase test, not in final exam.
This is the time when you're applying the limits, right?
Sorry?
When you're applying the limits.
No.
And can count.
So if, for example, this is your function, so for this function we know that a0 is 0 and an is 0. Why? Because this is odd function, right? And similarly, if you have this function, which is reflected about y-axis, so in this case we know that bn is 0. So if, for example, you have such question in exam, and if you have been asked to do full calculation, then you cannot write these. Means you have to do full calculation. But if nothing has been asked, and if you want to do, then just write the reasoning that okay, an is 0 because this is even function. This is this. That would be sufficient.
For Fourier transform, is it Fourier transform for the Fourier functions like?
You want me to give you a question? Yeah. Just try to solve what I have. If you are doing your tutorial, if you are doing your class that I am solving in class,
That's
would
a very good question. You know, all the good questions will be similar to tutorial that you gave us. Right? I mean, similar, I mean the same style. I mean.
yeah. So if I'm saying that
That's the same.
if you are following my examples in class that I am solving with you on board,
Yeah.
and even if they are on slides, and if you are following tutorials,
Yeah, that's it.
your life will be.
Thank you very much.
Thank you.
I will see you in a bit in.
Thank you, sir.